So this morning, I know we did it in lab, we've talked about it, but I want to revisit series and parallel for resistors, do a quick example on that, and then we'll talk about magnetic fields and magnetic forces and magnets. Okay. So resistors, there's a couple of problems in the homework. I think they're pretty easy. Resistors in series. Sort of back to back, one after another, however you want to say it. That would be a series connection. Well, you can have any number in series. Resistors in series have equal current. They have one common connection. The other connections go elsewhere. They have one and only one common connection. Okay? And the equivalent resistance, I'm just going to write it down. R equivalent is equal to R1 plus R2 plus ... as many as you have in series. You just add them up. So the series resistance is always greater than the greatest resistor. Maybe that's obvious, but I don't know. Sometimes it's helpful if you're doing a problem and you get an answer and it's less than, your largest resistor. You did something wrong. You did the wrong calculation. So, okay. They have equal current because, if you think about the current flowing in the circuit, whatever current flows through R1, there's no other path. It's a one-way street. It must flow through R2. Parallel. These connections are just like capacitors. Series and parallel refers to how they're connected, but finding the equivalence is opposite. Okay? So for parallel resistors, the connection is just like you would have with capacitors. All right, so here's R1, here's R2. Resistors in parallel have equal what? No. Voltage, yes. They're connected across the same voltage. If you put the meter here or here, that's the same connection. They have the same voltage. The equivalent resistance is calculated like this. 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus ... If you have two, I usually always do parallel, two at a time. I'll do two, and then if there's another one in parallel, I'll take that equivalent resistance and put it in parallel with the third one and keep going. So for two in parallel, it's simply R1, R2 over R1 plus R2. Okay? So the equivalent resistance is always less than the smallest resistor that you have in parallel. You're giving the current, no matter how small the resistor, if this is a 1 ohm and this is a million ohms, okay, you're giving the current another path to flow. You're lowering the resistance when you add resistors in parallel. If that's a 1 ohm and that's a million ohms, you're guaranteed that the equivalent resistance is less than an ohm. Okay. All right. So that's the 2-minute refresher on series and parallel. So let's look at a combination circuit. This is the same thing we did with capacitors. We're going to reduce till we find an equivalent resistance, and then work backwards using Ohm's law, which is V equals IR. That's Ohm's law. We're going to work backwards using Ohm's law, find all the currents and voltages. Okay? So here is the circuit. Let's see. I think I used even numbers for the 8 o'clock class. I'll use odd numbers for you guys. 3 ohms, 5 ohms, 3 ohms, 7 ohms, and let's put a 9 ohm down here. Okay. Okay. So the game is to figure out, okay, what's in series, what's in parallel, what can I immediately reduce? Find an equivalent resistance.
3 and 7 are in series, and those 2 are...
Yeah, the 3 and 7 are in series. I'll go ahead and draw the picture, a new picture for that. I mean, yeah, I know where you were headed, Will, but let's go ahead and draw this picture. Okay, so this is the 3 ohm, 5. The 3 and the 7 are in series, so this is a 10 ohm, and this remains a 9. Okay. Now what? This doesn't change. Yeah, the 10 and the 5 are in parallel. So, next picture. This is working out. So 3. 10 and 5 in parallel is 50 over 15. So that's 5 over, 5 over 3?
No, 3 and a third.
3 and a third.
Oh, 3 and a third, okay. So that's 10 over 3. Yeah, 10 over 3, yeah. And this is a 9. Okay. I think it's pretty obvious that all 3 of these are in series. Okay, so we just add them up. And that'll be our equivalent resistance. Oops. So what do you get here? 9, 27, 36, 46 over 3? Can somebody calculate that for me?
Yeah,
46 over 3, okay. I'll leave it like that. I'm going to need your help with the... All right. Okay, that's the equivalent resistance. You got one of the answers right. Okay, what is our equivalent? So now it's a matter of finding the current. Then once I know the currents, I can figure out the voltages. Okay. So what is the current here? It's 15 divided by, so it's 45 over 46. It's about 0.9798. Okay, what do you get? 0.98 what?
Well, 978.
Okay, 0.98. I'll let you guys keep the digits, okay?
That's IT, right?
Huh?
That's
the total current. Yeah, if that's what you're asking. All right. So that's the current through the equivalent resistance. That's the total current coming, out of the battery. This came from a series connection. So we're guaranteed that all three of these will have 0.98 amps. They're all in series. Resistors in series have equal current. 0.98 amps. 0.98 amps. 98 amps. Okay. So now I can figure out the voltage across each one of these because I know the current, I know the resistance, I'm using Ohm's law. So what do you get here? 2.9 something volts. Somebody give me the number here. 2.934 volts. Here, 3 point something. 3.26 volts. Whatever's left over, 8 point, what? 8.8 volts, good enough. Okay. Well, I'm finished with the 3 and the 9, but I know the voltage, I know the current. No more work to do with the 3 and the 9 as far as what we're doing. Now, this came from a parallel connection. Resistors in parallel have equal voltage, so this one has 3.26 volts. And this one has 3.26 volts. I know the voltage, I know the resistance, I can figure out the current in each one of these. Okay, so this one is 0.326 amps. And this one is 0.1 something. No, this one is what? 0.6. What do you get here? 3.26 volts divided by 5 ohms. 0.65.
0.65.
Okay. Amps. Okay. Just using Ohm's law. This is finished. I know the voltage. I know the current. However, this came from a series connection, a 3 and a 7. So these must have equal current. They must both have this current, 0.326 amps, 0.326 amps. And I can figure out the voltage on each one of these. This one's going to be 2 point what? 2 point what? 282. Okay. 82 volts. And this one is 0.9 something. 7 what? 8 volts. Okay. That's it. As you can see, when they're in series, since they have equal current, the larger resistor gets the larger voltage. Smaller resistor gets the smaller voltage. When in parallel, the larger resistor gets less current. The smaller resistor gets more current. Any questions on this method? Reduce, 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 find our equivalent, work backwards, find the voltages and currents. Questions on that? Okay. So that's it. We're finished with current, resistance, capacitance, power, electrical power. I wish I had time to talk about Kirchhoff and all his enormously fun rules. Some of you in circuits will experience Kirchhoff. Okay. So we're going to start talking about magnets. Okay, magnetism. Magnetism. Another one of our fundamental ideas in physics, or fundamental parts of physics. Tell me what you know about magnets or magnetism or anything you know.
Positive and negative attract.
Oh, positive and negative. I think you're talking about charges.
Polar, opposite
Polar. Okay, I like polar. What are the names of the poles?
pole.
North and south. Yeah, okay. Magnets are named differently. They could just as easily been named positive and negative, but typically called charge, positive and negative. They could have been named Ed and Bob, but what? Yeah, that would have been better, I think. Okay. Yeah, north and south pole. That's what we usually think about. So here's a little bar magnet. You know, a physical magnet like we're going to mess with in lab. We have a north pole and a south pole, so magnets are dipolar. And one of the very puzzling, interesting things about magnets is if you cut this magnet in half, you don't get a north and south like a single north pole and a single south pole. You cut it in half, you get this, north-south, north-south, okay? You get two dipoles. And then you cut it again, you get the same thing again. Okay? You cut it, slice it as much as you want, it's always going to be dipolar. You're always going to get a north and south. Meaning there are no magnetic monopoles. There's no like north charge or something that's just north. Like with positive charge, you have just a positive and the field lines radiate outward and you have a negative. Okay. Not so with magnets. As far as we know, there should be no reason that they can't exist. As far as the fundamental physics that we know, they just don't. As far as I know, no one's ever found a magnetic monopole. People have been looking for them for years and years and years, and no one's ever found one. People claim to have, you know, oh, we found a magnetic monopole. We flew an airplane in the upper atmosphere for 7 days and we discovered, okay. Nobody could repeat the experiment. Okay, there's some decent experiments that have claimed to have found it, but okay, they just don't seem to exist in nature. And there's an interesting argument by a famous physicist named Dirac who said that quantization of charge is not well understood either, why charge is quantized. And he has a pretty strong argument that if you could find a magnetic monopole, you could explain quantization of charge, but that's for a whole nother area, okay? So they're always dipolar. They always have north and south poles. What else do you know about magnets? Yeah, they're like charge in that sense, right? Opposites attract. And likes repel. Okay. Yeah, so you put a north and south together and they will attract one another. Two norths will repel one another. We're going to play around with these in the lab. Two norths will repel and so forth. All right. different kinds of sort of magnetism is generalized into pretty much three categories. Ferromagnetism, that means magnets like a permanent magnet that's sticking to your refrigerator. That would be ferromagnetic, okay, meaning steel, iron, they stick very well to steel and iron, and well, nickel is pretty close. Then there's paramagnetism and diamagnetism, which if we have time, we'll talk about. So the magnetic field, we'll talk about that. Here's that bar magnet again. The magnetic field lines always emanate from the north and they enter into the south. So they're like this. This is the best I can do. So they exit the North Pole and they enter in the South Pole. And they're always closed loops. So the field lines actually go through the magnet. Lots of interesting implications for those being closed loops. Okay? The field, the magnetic field unit is called what? Anybody know? Units of magnetic field or magnetic field density. It is a Tesla. Long before the cars. Okay. Magnetic fields are in units of Tesla. Well, let me tell you what a Tesla is. It's capital T, by the way. It is a Newton second per Coulomb meter. Okay? It's a Newton second per Coulomb meter. That's the fundamental units, or more fundamental. This is a Newton per amp meter, however you want to think about it. Okay? So a Tesla is really a field density, but that's the unit of magnetic field. We usually use the letter B to represent the magnetic field, B. Probably for Biot-Savart. We'll talk about the Biot-Savart law eventually. It is a vector, so it's a magnitude and a direction. Okay? If it's a field, well, you can have scalar fields, but this is a vector field, and you usually use the letter B. Okay. There's an older unit, and when I say older, I mean there's another unit that's used pretty commonly, and that's called a Gauss. G-A-U-S-S, named after Gauss. Okay, a Gauss is 1 Gauss is equal to 10 to the negative 4 Tesla. So there are 10 to the 4, there's 10,000 Gauss per Tesla. A Tesla is a large field. MRI, if you've ever had an MRI, they're usually 2 or 3 Tesla, okay? So they are, depending on how closely they want to look at you. 2 or 3 Tesla, something like that. I would say 4 max, maybe. In comparison to the Earth's magnetic field, which is roughly about a Gauss at the most, okay? So you're going from 1 Gauss, which is Earth's magnetic field, to 50,000 Gauss or so forth, okay? Tesla is a very dense field. But the Tesla works out in these nice, standard units, Newton second per Coulomb meter, okay? So we're going to look at the interaction between charge and magnetic field. So let's say that I have a uniform magnetic field in a region. They're always closed loops, but you can make uniform fields in a small region. So the little x's mean that the field is into the board. So an x is into the board, and an O with a little dot or just a dot is out of the board. Okay. So that would be a vector going into the board. That's a vector coming out of the board. So I have this uniform magnetic field that is in this region, and I'm going to place a charge in it. So here's a little positive charge. Here's Q, and it's positive. Okay. If it's a positive charge, or any kind of, it doesn't matter, positive, negative charge, and it's sitting in a magnetic field, no interaction. Okay, you have to have a couple of things happen before you get an interaction between charge and magnetic fields. If I give this charge a velocity somehow in that direction, so I'm saying that the charge velocity is in the plane of the board, okay? So if I look at this with a, from the top, look down on this, then V is in that direction and B is in this direction. Okay, that's a top view. So the angle between V and B is 90 degrees. Okay. In this case, the way I've drawn it with that angle 90 degrees, there is a force between the charge and the magnetic field due to the relative motion of the charge in the magnetic field. And the way you figure out the force direction is with the right-hand rule. And there are several right-hand rules. Okay, this is the first one that we'll learn. People do these right-hand rules differently. Different professors teach them differently. This is the way I do it. Okay. First off, you have to have a right hand. Does anybody not have a right hand? I had a student who did not have a right hand, and I had taught him the left-hand rule. But okay, we all have right hands. You have to know which hand is your right hand. Okay. Now that may seem silly, but I see students all the time on a test. They're writing furiously and going like this. They're using their left hand. They're getting all the directions wrong. But that, Okay. This is a right-handed coordinate system. Index finger, that's the one you point at people with. Middle finger and thumb. Okay. So this would be like X, Y, Z. A right-handed coordinate system in 3 dimensions is like this. This would be X, this would be Y, and this would give you the proper direction of Z for a right-handed coordinate system. So, yeah. So in this case, this is the velocity. You point in the direction of velocity. B is your middle finger. So the middle finger is magnetic field. Thumb is force. Okay? So in this case, V is in that direction, B is into the board. The force on the charge would be up. You can always, I know, you try to figure out the best way. Yeah. You can move this around. Some people teach it like this and this and this. I don't know. But this is the way I do it. I can move this all around. Okay? So V, B into the board, that's F. So you would get a force in this direction. Okay? If the charge is negative, you flip. So if it were an electron, this is the way I do it. Some people will tell you to do it with your left hand. I won't. But if you do it as if it's a positive charge, if it happens to be an electron, it's negative, you flip. The force flips.
So with that also, so don't worry about the exit, just you worry about the position of the charge. 'Cause that's-
Right.
okay.
Yeah. No, you make this fit your coordinate system.
So
Yeah, if V were in this direction and B were out of the board, or if V was that way, B, okay, this way, okay, this way, I mean, yeah. All right, that gives you the force direction. The force is a vector, we all know that. And it's given by QV cross B. This is, and I don't, I'll do a lecture on the cross product. But this is the so-called cross product or vector product. It's a way of multiplying two vectors and the output is a vector. Remember with the dot product or scalar product, you multiplied two vectors and the output was a scalar, give you a number. This gives you a vector. The magnitude of F is equal to QVB sine theta. The dot product is cosine, the cross product is sine, where theta is the angle between V and B. That's theta. So you need charge. You need the charge to be in motion, and you need a component of the charge to be at a right angle to the magnetic field. Because if V and B are parallel or anti-parallel, and we're going to play around with this in lab, if V and B are this way, then the angle between the velocity and the magnetic field is 0. Sine of 0 is 0. No force. It's the equivalent to the dot product where you had the force vector perpendicular to that displacement direction. You got no result. You got a 0. In this case, if the velocity vector is in the same direction as the magnetic field, or anti-parallel, no force. Okay? We'll talk a lot more about cross products. All right. So you can see where this unit of a Tesla comes from, right? If you solve this for B, you get Newton per Coulomb and then a second, what is that? Yeah, Newton second per Coulomb meter, right? If you solve that for B. Okay. I'm going to redraw this over here. We'll do sort of a calculation based on this. All right, here's the magnetic field, B. Here comes an electron. Because this is what we're actually going to do in lab. Here comes an electron at some velocity V, at a right angle to B. As the electron enters the field, it's going to experience a force. And that force is going to make the electron go in a circle, okay? You can kind of ignore, yeah, okay, maybe there's some. Right. The velocity in this case is this way, then it's this way, then it's this way, okay? The magnetic field can do no work. It can't speed up the particle or slow it down, but it can change its direction. Magnetic fields do no work, ever. You may say, you see these big magnets, if you've ever seen big magnets picking up like cars and stuff and big pieces of steel. Oh, my magnetic field is working, it's doing work, force through a distance. No. Okay? We'll figure out eventually what's actually doing the work. But the magnetic field can definitely produce a force by changing the direction of a particle. That force is always at a right angle. I'm going to call it FB. I don't know if y'all all can see this, but should have drawn it bigger. But that force is always at a right angle to the velocity and the field. Because V and B form a plane. Two vectors form a plane, okay? The force is always normal to the plane formed by V and B. That's how the cross product works, okay? So if you form a plane with V and B, the force is always going to be perpendicular to V and B. That's that right-hand rule thing, okay? F, in this case, FB is equal to EVB. That's the charge on the electron, that's the velocity, that's the magnetic field. I'm saying that it's like I had over here, the angle between the field and the velocity vector is 90 degrees. Okay. We know from what we did in physics 1 that for uniform circular, this will be uniform circular motion, right? The particle's not speeding up and it's not slowing down, it's just going in a circle. We know from what we did in physics 1 that the centripetal force is mv squared over r, where that's the centripetal acceleration, that's the mass of the particle. What's providing the centripetal force? The magnetic force, right? That is the centripetal force. That's the force that's causing the object to go in a circle. So I'll equate these two. You get EVB is equal to mv squared. Oh, I usually use a Q here. Let me, it's okay, we'll use E. Did I get the direction right? I hope I did. Yeah, okay. Scared me for a second. I forgot to check. I've done it 10,000 times, so. Yeah, that would be the force direction if it were a positive particle, so you flip. Okay. EVB is mv squared. We get V cancels, and you get, I'm going to solve this for R. R is equal to mv over EB. Just think of that as, I think I wrote a Q in the other class. It's more generalized with Q. I made it an electron. It could be any charge. It could be any charge, a particle, a proton, an alpha particle, whatever it is. Okay? This is an important result. We'll do a lab based on this result because when the electron was discovered not too long ago, one of the first things that was measured was the charge to mass ratio for the electron. So they could easily, knowing the field strength and so forth, you could measure the ratio of charge to mass for the electron. Okay. Eventually, the mass of the electron, charge were measured independently and so forth. Okay. So looking at this, depending on the mass, you increase the mass, you increase the radius of this orbit, you increase the velocity, you increase the radius, you change the charge up, increase, decrease, change the field. So it's dependent on those four things. We can make a substitution here, knowing that V, when I'm writing V, I hope you realize, in this case, that's the tangential velocity. So that's that tangential velocity of the orbit. All right. V is equal to R omega. Remember omega? That's that angular velocity or angular frequency. Okay. V is equal to R omega, so you can make a substitution here and you get omega. What do you get? I'll just do it. R is equal to M R omega over E B. These R's cancel and you get omega equals what? EB over M? EB over M. That's also an important result. Because if you can somehow calculate that, you can figure out what the angular frequency of the orbit is just by knowing the charge, the field size, and the mass of the particle. Independent of velocity. The angular frequency or angular velocity is independent of that tangential velocity. Okay? Also, T is equal to what? 2 pi, wait, I have to start from the other way. V is equal to 2 pi R over T, right? So we can use that, and you get R is equal to M 2 pi, what do I want to solve for here? 2 pi R over EBT. R goes away, and you get the period. T is equal to what? 2 pi M over EB, right? I think that's right. So that's the period of the orbit, independent of V. I don't think I have time to do an example. Let me show you. Okay. I got 2 minutes. Maybe I got time to show you this. There should be. That's pretty good. Ooh, I like that one. I don't see the one that I usually look at. Well, this is not too bad. That's the one. Oh, I want to show it. What do I do?
right. Hold on. Let me change it.
Yeah. If it'll do that. Oh, great. Okay. That's good enough. Okay, this is called a cloud chamber, a clever little old-timey device. You take ice and you put this little chamber on ice, usually dry ice, so solid carbon dioxide. You put some alcohol in it and you make clouds. And then you let charged particles go through your clouds and you can see the tracks. So you also have a magnetic field in the region. So this would be particles that were entering the cloud chamber, and you can see you get these nice spirals. Why are there not these nice, uniform circles? Why would there be spirals like this and so forth?
Does the angle change?
Yeah, the angle's changing, but also the particle's losing energy. It's moving in the clouds, okay? The little contrived example that I did was in vacuum, where you have this nice, no loss of energy. Plus, you also get a helix. If there's a component of the vector that's, say, along the field, the particle will spiral in the field like a helix. What are the straight lines? Huh? Could be. Anything else you can think of? A neutron walks in a bar, orders a drink. He asks the bartender, how much do I owe you? Bartender says, for you, there's no charge. Okay. Yeah, so these are particles that are not charged, right? They just go straight through. Okay. All right. See you next time.